Hi, I'm Philipp. I'm talking about full text search and what you can do with that basically and how to get started. So I work for Elastic, the company behind Elasticsearch, Lowercase, Beats, like lots of open source products. I'm part of our infrastructure team, so we do stuff like Docker, AWS, Jenkins, testing, lots of that stuff. And I always say this is a Unix type, I kind of hype that up into developer and testing. So I talk about all the good stuff we do at lots of conferences and meetups. So who uses databases? I guess it's pretty much everybody, right? Good. That's a good start. Who uses search already? That is also quite a few. Who uses Elasticsearch already? Yeah, very nice. Who uses something else? Okay, there are some. What are you using? Who's using Solar? Okay, anything else? Okay, so while I will be talking about Elasticsearch itself, like the concepts totally apply to Solar or anything that is based on the fetching scene as well. So at least the concepts you can totally take away. The queries might look slightly different, but the concept and how it works behind the scenes is totally the same. And just to, before we dive into the, I wouldn't say dry, but like the action of how to actually query stuff and how it works behind the scenes, this is more of a motivation of like, what is full text search exactly, why is it so complicated, and what can you do with that? So we have a quick demo application we wrote. Yes, my Turkish is not that good, unfortunately, and I'm missing a thank you. Yes, I need you. So, no, that's very weird. Yeah, let's use it like that. So we have a demo application. If you try to read the URL, unfortunately, you cannot because it's password protected. Because while we wrote the application, the data is not owned by us. That data is provided by Zalando, but you can only use it for demos. Unfortunately, you cannot use that. But they just gave us lots of data from their web shop, and this is just to motivate and show what is actually going on behind the scenes. So often when people closer, okay. Even closer. Let's see. Hope that doesn't get closer than that. So what often happens if you go to a web shop, the first thing is you just start searching. So in my example, I will just search for a white shirt. And then it will automatically suggest you some stuff you can do. And while this looks very much like a regular shop you can use, we have this little wrench tool here. And this will actually show you what is the query that you've done in the background. So by that you can actually see what we have done. And you can see we're doing some suggestion for my specific user for white shirt. Then my first completion just went on for shirt and then it said picture. So these are the queries that are happening in the background. And when I actually run that query, it will give me some results. And I'll make this a bit smaller so you can actually see what's going on. Are these great results for white shirts? Probably not. So that already shows like what the problem of full text search is. Somebody enters some text, and then you kind of not only need to kind of find what they put in, but you kind of need to guess what did the user expect to happen actually. And in that case, it's not great. But that could be the result if you just search for white shirt. So luckily, we have some additional tools around here. So here you can basically see the settings, how did we actually search for the stuff that came back. And in that example, we're basically searching for the term white shirt over lots of different fields because we have a title, a description, we have tags, we have probably like the material the stuff is made of. So we have lots of information there. And right now, our query is using the query title to search over multiple fields called best. And that basically just selects one of those fields and just searches on that. But what we probably want is, we want to have our search term white shirt in as many fields as possible. So I just switch that over to most, apply that query now, And then you can see the search results are getting better again. So basically you have lots of information and you can run lots and lots of queries against that. But what the actual quality of your results will be very much depends on what do your users expect and how does that translate to actual queries. We'll go into a bit more of these details later on. Just something else we could do. So for example, we could say that the description is 10 times as important as the name, for example, of the product. And when I search for that, you can try that again. You can see that is not improving my search again. So you can weight the fields, but probably depending on what data you have, it's getting better or worse. So I can invert that again. And I can say I'm searching for white cotton shirt now. Let's see what we get here. It didn't apply that. Oops, no, 0 is not what I want. Let's apply that search again. Let's see what we get for white cotton shirts. And you can see, yeah, that is very nice already. We get some other fields which we don't want. Luckily for my search, everything is for male categories. But you could, for example, your search, since I have a user profile and I have specified my gender in that, your search might include in the background actually what gender should those products be for. And you can actually see what is going on. So here we're just seeing the results. We have something called the request. So this is the actual Elasticsearch query, which is more complicated than what we'll cover today because it's a lot of stuff. But if you scroll down here, at some point you will see that there is the white cotton shirt. If I find it. The white cotton shirt will be somewhere. Yeah, here we have the white cotton shirt. And here you can see these are all the fields which we have searched basically. So while it looks all very simple, it can get tricky in the background. And we also have this response field. So this is actually what Elasticsearch will give you back. So these are all the responses, and that's what we're using to generate the site. So now that we've seen how to actually use it in general, let's jump a bit into how does that work behind the scenes. So yeah, we've seen that. That was kind of like what we searched for. What makes databases and full-text search so different? The first thing is, with full-text search, you do lots of more work when you store the actual content. So what stores your data on disk is Apache Lucene. There is no other database or data store behind it because that's a very frequent question. What actually stores the data on disk already is Lucene. And Lucene is doing all the hard work around searching. What Elasticsearch around it is providing is provide the REST interface, it provides the query DSL, and it does the distribution and replication of the data in the background. So you don't need to care about that. But the actual search part we will mainly focus on is what Lucene is doing. If you want to run all of these examples I'm showing you yourself, you can easily do that. Like we provided hosted in the cloud. So if you just want to experiment with Elasticsearch quickly, you can run it in the cloud. And the other thing that everybody needs to do is Docker right now. So yeah, of course, we can do it with Docker, even though I think the Docker should actually be this one. So Docker will leak you in your application at some point. But to run what I'm doing here, that would be the easiest Docker Compose file you can do. So we have Elasticsearch 5.4, and we have our own registry, and we simply run those two containers. So I use Kibana, that is our visualization tool, to run the queries, because it's, as you will see, it's nicer to interact with than just using plain curl. And we're using Elasticsearch. So that is the minimal setup you need to have to actually try it out for yourself. So, who knows stars? What is the quote here? Yes, these are not the droids you're looking for. And I've added this emphasis here so that they're not. So this will be our example text. And we want to actually store that in Elasticsearch and see how that is being stored and what remains. So what the first thing you normally do is you throw out the HTML or any other formatting. Because nobody is going to search for this EM nobody is searching for that. So we simply kick out any formatting we have there. The method we use is HTML strip, but it doesn't really matter. So we're just stripping out any formatting. The next step is we tokenize it. Tokenizing in most Western languages is very easy. You take the white spaces and the punctuation marks and you split the words on those. So you can see I've added a bit more space where you can see one token is these, are, not, etc. If you're doing Chinese or Japanese, stuff gets more complicated and weirder. But since I have no real clue about those languages, we'll skip that. So we just assume any space dot, you see the dot at the end is gone as well, is where we actually split up into the tokens. And Elasticsearch doesn't really understand your text. It's just operating on these tokens from now on. The next thing we do is lowercasing. Normally when you search for something, if you type into Google, you don't really care about upper and lowercasing. But since it's two different ASCII characters, and you would need to search for both of them, we're just getting rid of the upper and the lowercase, and we're lowercasing everything, so this is what we'll store in the background. The next thing we'll do is we'll do the so-called stemming. First we're kicking out the stop words. So everything here, like you have a lot of words which are very, very common. And they're pretty much in every text. So they add very little meaning to your text. So we'll just throw those out. So for example, pretty much every English text would contain R. So we'll get rid of that. And some others. So these are not the droids you're looking for. The only thing that passes through the default stop word token filter is droids you're looking. Everything else gets removed. You could provide your own list of stop words. You could remove stop words like any removal in general. So you don't have to do that, but for many languages, for all the supported languages, there is a list of these stop words which makes sense for most of the cases from a lingual point of view. And then we do the stemming. So the stemming is basically cutting off, at least in English, the end of each word to reduce it to kind of the root of the word. Because you normally don't care, am I searching for droid or droids? You don't really care if it's singular or plural. And sometimes you don't really care about is it beauty or beautiful, like the noun or the adjective. You don't really care about that. You just care about the concept. So the only thing we will be storing in the background from the sentence, these are not the droids you're looking for, is droid you look. Just these three tokens. And you can actually try that very easily. So let's just do that live, since it's always more fun to do everything live. If I find the tab. So this is Kibana that is very easy to interact with Elasticsearch. So if you would do that with curl, you would do curl xcat localhost 9200 slash to actually get any result out. We're just removing that, we're just doing get slash or whatever to interact with that. And that has syntax highlighting and auto completion so that we do everything for you. So if I run that, these are not the droids you're looking for, and I run it against the underscore analyze endpoint, it will not store anything yet. It will just show me what tokens would remain after I run it through. And you can see these are the tokens I get back. So like I told you, droid you look, that is what remains. So it will actually know where are these, where's the start and the end offset. That is very important for highlighting. So if you want to highlight the hit, if you have searched for droid, and you want to easily highlight the word droid in your text, since we have the start and the offset, you can easily highlight that in your text. We know that it's of the type alphanumeric. If you have Japanese, that would be different. And we have something like the position. The position will also be stored. That will be important if you search for a phrase. So if you search for the phrase droid you, which is a weird phrase, but it works for that example, you say make sure that you have droid in your text and you have the first has some position and the other word has the position right after it. And since we explicitly store that position, you can very easily search for these phrases afterwards. And you can actually specify all of these steps. So previously we just relied on the defaults. Here I'm just saying what I explicitly want to have. So you could switch out the tokenizer. I'm relying on the standard. I'm saying I want to lowercase everything. I want to remove the stop words. I want to do the stemming with the stemmer snowball. Even before that, I have removed all the HTML, and that is the text I want to test against. And this is giving you the exact same result, just the EM has been removed as well. So draw it, you look. Okay, so this should be the same phrase in Turkish, right? General agreement. What do you think remains if I run that through the Turkish analyzer? Yes. Since I cannot pronounce it, I will just show you. That is what the analyzer will leave out. So you can see the first word seems to be a stop word, and the next three are not stop words, but there has been some stemming going on.
And the first word is actually in past tense.
Okay.
But maybe you should, because if you stem it, it should be just ara.
Yeah, so generally some people talk about stemming, other about lemmatizing. So the difference is generally stemming is very simple. It's just based on rules. So you have very few rules. If you use proper lemmatizing, you would have a dictionary in the background. And only with the dictionary, if you have if you have the past tense, and that is very different to the present tense, only with a dictionary-based approach you would normally find that. So it's not really doing lemmatizing, it's just doing kind of very simple rules. So in English, it's normally just cutting off the ending, basically. Another thing that can happen is, what happens if you use the English analyzer and use a Turkish text? Yeah, it will not really fail, but it's just like, it's not giving you the results that you expect. Yeah, for example, it's nearly the same words. You can see here the LER. Then it seems to be like a stemming rule in English, so that's cut off, but it doesn't make any sense anymore. So you really need to know which language is my text in, and how do I need to analyze that. Yeah, if you're interested in the Turkish stop word list, it is hidden deep down in Apache Lucene, but yeah, you can find it if you're looking for it. One common question is like, what if I don't know what the language is that my text is in? So one of my colleagues has written a plugin for Elasticsearch that can actually detect, or, well, it's not 100% foolproof, but it can run some detections and it will try to know what is your text. So if you don't know what the language of your text is, you can add that plugin, test the string you have first, and then use the proper analyzer for that language. Otherwise, if you don't know the language, Elasticsearch cannot help you. It's not solving that problem for you. Language-wise, that is what we supported in 5.0. Turkish is in there, lots of the Western European languages, though some are missing. So for example, Slovenian and Slovakian, where I'm quite frequently, they're not there, they're just not supported yet. How would you get in another language if you want to add a language? The process is normally, you need to add it to Lucene first, then Lucene does a release at some point. Then we can add the APIs in Elasticsearch. So for example, Ukrainian was added in Elasticsearch 5.1. Before that, it was added in Lucene 6.2. And to actually only expose the endpoint is not that much work. There is one pull request to show you. So for example, if you go to Belarus and they don't support Belarus, it doesn't support Belarusian yet, what they would need to do is they would need the patch for Lucene and then expose it in Elasticsearch. And the language rules are obviously very language dependent. So for example, in English, if you have this apostrophe S, which could be the possessive, is or has, that is just cut off. In French, you would, for example, cut off stuff at the beginning because this is just the article. And you can see the accent is also. In German, we have these weird umlauts and this S thingy, so that is basically flattened out. So the umlaut is just the dots are removed because it's basically the same letter. And that special S thing is just scaled down to a double S. But this will totally depend on your language. So for Turkish, you probably have different rules for that. But we'll stick to English now so I can anticipate it as well. Obi-Wan never told you what happened to your father. Any guesses what will happen if I run it through the same pipeline? Yeah, there are not that many software. So the standard analyzer will actually take the hyphen and make two different tokens out of that. So we have OBN1, and then we remain with never told you what happened your father. No, I am your father. Any guesses? What remains here? I am your father. So no is a software that is removed, but since it has no dictionary, it doesn't know that am, be, is, whatever is the same thing. So it just keeps I am your father. So this is what would be stored in that example. And what would be actually stored in the background in Elasticsearch is we would extract all of these tokens in the stemmed version, and we would mark them how many times do they appear in a specific document. So assume like 3 examples where they have the IDs 1, 2, 3. We would store like how many times do these tokens appear and what was the position of that token in the text. And that is what actually Elasticsearch stores, and that is how you can very efficiently look stuff up. So if you, whatever you're searching for, that is run through the same pipeline, analyzed in the same way, and then it just looks up on that list that is sorted alphabetically, so that lookup is pretty cheap, which documents contain look. And then you see look is in 1. Or you could search for father and I, and then you can search for both of them, and you can see father appears in the document 2 and 3, but only I only in the 3rd document. So if you AND connect those two, it's basically a big set. You can AND connect them, and you see only I and father appears only in the 3rd document, and that's what makes these lookups very efficient. So we can actually now store stuff. So far we've only analyzed it, we want to store it now. The first thing which we're adding, which you don't get in a database as well, for example, is synonyms. So I want to be droid and machine and father and dad to be equal. So we'll store that as a synonym. I store it as my synonym filter, then I have this pipeline again, and I say, do all of these steps, and at the very end apply my synonym filter. So where there is father, also store the word dad and point to the same place. So it's just a synonym. We store that under my analyzer, and then we just say I have something, the attribute quote is text, and it should be analyzed by my analyzer, which I've just shown you. Let's just do that since we'll do more of that stuff live now. So that is my mapping I have created. And then I can insert my 3 quotes we had before, so you know what these will end up with. So we have inserted our 3 texts now. You can very easily retrieve that. So if you just say, I've stored it under Star Wars quotes ID 1, I can simply return the entire document, and it will actually tell me some additional information. So it knows, okay, that was stored in that index, in that type, under that ID. And I've just stored it once. Every time you would store it again, that version would be incremented. We found something, and that was the original document we had. If you just want to use it like a data store, you could just say underscore source, and then you would just get back the original document you had stored. You can do that, but that is not what the power of Elasticsearch is really about. Let's do some searching. So if I have this query here, what would be the equivalent in SQL? Select star from star. So if I run that, I should get my 3 documents back, and indeed it has some more meta information, but it tells me in total I had 3 documents, and these are my 3 hits I get back here. So that's also not very exciting. Let's do some proper search. If I search for query, so the syntax is slightly unexpected, but yeah, that's the way it is. So I do a query, I say I want to match on the attribute quote, and I'm searching for the text droid. How many results should I get back? So we had 1 total hit, and these are not the droids you're looking for. So that was the only text. And you can see I'm searching for droid, but I'm finding droids, but thanks to the stemming that is very efficient. What do you expect if I search for dad? How many results will I get back?
0.
Like so many options. No, it should be 2. You see, we have 2 results, and actually we found I am your father, and Obi-Wan never told you what happened to your father. Here we have the synonym. We have the synonym father and dad. And since I'm searching for dad, it's kind of the equivalent, and so we're finding both these documents that contain father. We can also do a phrase search. So we can search for I am your father, and we'll find the phrase I am your father. If I search for that here, that is getting more tricky. So what the phrase search basically says, I need to have all of these words, and exactly in that order of the words. And then I can say, I can add some sloppiness to my query, and I can say, there could be something else in between. But all of the words I have here still need to be in my document. So if I'm searching for I am not your father, will I find anything or will I not find anything? Sorry? I am your father. Slop is one. So let's try that one and see what happens. So I am your father, I find it. Let's do I am your good father. Should this also be found? So suddenly that is not found. That is very weird, right? Any guesses why I am not your father and I am your good father are different?
Because it's removed.
Yes, exactly. Not is a stop word, so this is basically removed. The sloppiness tells it there can be something missing, like there can be a difference between the phrase you're searching for and the final result. But all the terms that you have in your phrase search need to be in your result. So that is kind of a tricky one. And when I tried it out myself, at first I was confused as well.
Why did you query I am your dad?
I am your dad should work. I am your. We keep the right phrase, it will work. Will that work? Yes, that works as well, but only because of the stop word. So that is tricky. Another thing is, if you don't know how to spell something, so I didn't know how to spell Obi-Wan, and I spelled it like fun. We have something called fuzziness, and then it can just make sure that even if there is a slight difference, you can still find it. So if I search for that, it finds it. Obi-Wan never told you what happened to your father. And even if I have, you can either leave it to auto that value, then the auto will be determined on how long is your search string. So if your search string is 0 to 2 characters, the fuzziness will be 0. If it's 3 to 5 characters, it's fuzziness of 1. And more than 5 characters is fuzziness of 2. And fuzziness basically means Levenstein distance. So Levenstein distance is there is one character different, one letter missing, or one letter too much between what you have and what you're searching for. That is the Levenstein distance. Another tricky one that you would not expect probably is if you define a fuzziness, both auto or a specific value. So here I search for fuzziness, so one difference. Will this match or will this not match?
No.
Yeah, that is another tricky one. Because, yeah, so first, if you're using the standard analyzer, this will be 2 tokens. Because the dash is removed, then we get 2 tokens. And the fuzziness is applied per token. So you need to know how is my text analyzed and how do these functions work in the background. Otherwise, it can be, yeah, very unexpected results, basically. And, oops, no, I don't need to now. No, go away soon. Yes. Let's jump back into some theory. So, in the beginning, we had fuzziness, and people were like, okay, how does this work? And in the beginning, it was implemented kind of in a stupid way. It was just brute forcing. Basically, it calculated all the possibilities of permutations. So if you have a fuzziness of 2, you can guess that this is like a lot and a lot of permutations that you want to search. But it was rewritten. We're using now an Einstein automaton, And there's actually a story that there was a paper, and nobody really understood the paper. And then they found that somebody had implemented it in their free time in Python, and then they basically took the Python implementation and ported it to plain Java. And nobody really understood why it was working, but they could test it against the old implementation, and indeed it worked, and it was like lots and lots, like 100 times faster. So what the automaton looks like is something like this. So if you search for the term food, for example, and you have a fuzziness of 2, you can, in every position, you could have 2 differences. So you could either get like every line that is like if you go horizontally, there is a good match of a letter or a character, and if you go up, it's kind of like one of the 2 differences you could find. So if you could have food right away, and then it doesn't really matter if anything is coming after it or not, or you could have F, then any other letter, and then you could have food, then you would also end up in the result. So this corner, like you just need to find the right path through this Lebenstein or automaton to get to the final top right corner, and that is how it is calculated now. So that is kind of a very clever approach. Or you could, of course, in SQL, you could do that, but you can guess how fast that is and how much fun you will have writing that. The other thing which we have pretty much ignored so far, if I switch back to that again, we always have this score thingy here, which has a very weird value. And that is basically the quality attribute of how well does what you have searched for match with what you had in your documents. And how to calculate that is the scoring. So the general idea behind it is TF-IDF, term frequency inverse document frequency, if you search for one term. The implementation has now changed, been changed slightly. It's called, I always forget, is it best match or better match 25? So this is basically another algorithm and the 25th implementation of that one, and that is now the new default. But it doesn't really matter, like the concepts are still the same. I will show you how it's calculated. The first thing you have is the term frequency. Term frequency assumes you're searching for father, for example, and the text that contains father 5 times is way more important than the text that contains father only once. So to draw it out, you can see TF-IDF and BM25, like the curves are slightly different, but the concept is the same. Like this is how many times does your search term appear, and this is then how well or how much the match is contributing. So if a term appears once, you have probably a value of like 1 or something. So it's not that great. But if your search term appears 5 times, you can see the quality is higher. And TF-IDF kept growing, so if the term was in there 20 times, it still was more important. Whereas in BM25, we say like, well, if it's there 10 times or 20 times, it doesn't really make a difference anymore. So it's pretty flat after that. But generally, the more often your search term appears, the more important it is. Then we have inverse document frequency. Inverse document frequency basically says terms that are very rare over all your documents are more important than terms that are very common. So for example, if you have, to stay with Star Wars, if you have father, father is appearing very rarely in the Star Wars movie and mostly at the end of one, and is also very important. Whereas other terms which appear very often, they are not as important. So to see it in the curve, that is like how many times does the term appear overall over all the documents. And you can see if it's just a dozen of times, the term is very important. Whereas if the term appears hundreds or even thousands of times, it is not important, and BM25 after 1,000 will actually say like, well, that's so common, I don't care about that one anymore. And then we have the field length norm. The field length norm is also very intuitive. It assumes you have a field, and the shorter the field is, and you have a match there, the more important it is. So you just take the number of terms in one field, and divide 1 by that number of the square root, and that will give you how important that term is. So if you have the subject of an email, the subject is probably very relevant if your term appears there. Whereas if you have a very long text body and you have hundreds or thousands of words there, having the match there is less important. And the field length norm is actually doing that for you. And then you can put all of that together. So you can boost specific fields, you combine all of these factors, And at the end, your score will be calculated for you. So for example, you can actually see how it is done. If you add question mark explain to it and we search for father, the query will be actually explained to you. So it will then tell you, okay, the score you got was 0.41 something, and then you can see the IDF and the term, so the inverse document frequency was this, and part of that was the term frequency is that value. So if you do not know why something gets a specific score, you can actually add this question mark explain, and it will tell you, okay, these are the reasons or the contributing factors how you got to that score value actually. So let's assume we're searching for I am your for father. We're searching for father, and we're getting 2 hits back. We've seen that already. One has the score of 4.1 something, and the other has 3.9 something. Why is that one rated higher than that one? Yes, it is shorter. So the term frequency is the same. Both contain father once. So the term frequency is the same. The inverse document frequency is also the same because we're just searching for father, so that doesn't make a difference. The only difference here is the length, and you can see this contains fewer tokens than that one. Difference is also quite minor, but that is the only difference why that one is rated higher than the other one.
Are these scores out of 1?
Sorry?
Are these scores measured out of 1? Amount.
No, this is not one. That can be higher than one. So also do not compare the scores between different queries because it's probably not comparable. Since you have the inverse document frequency, it really depends on the fields. So you cannot really compare the score of one field very well to another field. So you need to be careful what to combine with that. So only see this kind of as a relative factor, but don't take this value as an exact and compare it between different fields. So this is just within that one query. This is how well that matches or how well it doesn't match. And all of that was just for one term. So how do you know if you search for multiple terms, which one is the best? We have something very fancy called vector space model. So you score each term, you vectorize it, and you calculate the angle. That is, sounds very complicated. I can show you that is easier. So we're searching for your and father. The best match would contain your and father. But we're interested in which document should be rated higher, one that only contains your or only father. So the assumption is that father is very rare over all our documents, and your is very common. So we can have, this axis is basically your father, this would be the perfect document, it contains both terms. And then we have the axis of your and father, so we have drawn that one. And since your is so common, we have given it kind of a random value of 1, so it's not that important. Whereas father is much more important since it doesn't appear that often, so it goes much higher here. And then this would be the perfect match. And then the question like, is the document just containing your more important or just father? And you can draw the angle here, and the shorter the angle is, the more important it is. So that will actually tell you, if you just have a document which contains your father, that is more important than a document that just contains your because the angle is much different. Yeah, and you can have very complicated functions there. You can have geolocations, decaying stuff. You can script it. You can add weight. So you can go pretty deep down there. So for example, one thing you could do is you could add a random score. That is only really helpful if you just want to get a sample of your data. If you have thousands of hits and you just want to get a random sample, you could do something like that. So you're just getting a random element here. There are lots of more features. The only one I really want to show is how to highlight something. So if I add that, I have my search query from before, and I say I want to have, before that, I want to add tags, and after that, tag. I just want to highlight that. It would give you the result back. No, I am your father, and I am your father, and the father has these tags, so you could easily highlight that in your results. Would that work with that? Yes, it will work with that. Since it also knows the start and end point of father, it would know where to actually put that. it would just replace it and show you what is going on. Okay, that is kind of back to the shopping example. You can see instead of a single match, I'm using a multi-match, so I'm searching over all these fields here. That thing here basically means I'm not boosting it, I'm just using the default value of 1. If you want to make, for example, the product name in English twice as important as the other fields, you could say, you could put a 2 here, and then that one field would be more important than the others. And what I'm then saying is I'm querying for white shirt in my example. At least 50% of my query must match, so either white or shirt need to be there, ideally both of them, and we're just interested in the best field. So that was the example we have seen in our shopping example in the very beginning. So basically it's the same concept, it's just adding a few more constructs around syntax-wise. Yeah, we've seen throughout formatting, tokenize your tokens, lowercase, stop word, stemming, and you can optionally add synonyms. That is kind of the storing part when something is stored. That is what a relational database does not do. This is just what is done by full-text search. Then we have the scoring. We have seen TF, IDF. We have seen the field length string plays a role. And if you have multiple terms, you need the vector space model where you actually calculate which one is the best. And just as a general pointer, if you do the analytics space, since I don't have enough time, I'm not doing that for that example here. But we're using our stack, for example, to see how have visitors rated our product, so which defects have been there, and what were the reviews, like how well were the reviews of our product reviewed. So it's not just for the full-text search part, but also for the analytics part, you can store that in the same engine there. Any questions? And before you run off, I'm always taking a picture, so I can show my colleagues that I've actually been working today. Smile, everybody. Yeah, very nice. Any questions?